All right, welcome to the deep dive.
Yeah.
You sent us this research paper. It's called One Instructional Sequence Fits All, a conceptual analysis of the applicability of concreteness fading in mathematics, physics, chemistry, and biology education.
Mm.
It's by Tommy Koklonen and Leonard Schock, and it was published in Educational Psychology Review back in September 2021. So let's dive in. This paper really tackles this idea that's pretty popular in STEM education, that the best way to teach is by starting with really concrete examples and then gradually moving towards more abstract concepts.
Yeah, you're absolutely right. That's what they call the concreteness fading sequence.
Exactly, concreteness fading. And you see this all the time, right? Like you start with hands-on activities, and then eventually you move to symbols and formulas and all that.
Yeah, it's kind of this common belief that this gradual shift, starting concrete and fading to abstract, is like this universal teaching method that works for any science subject.
So the big question we're going to explore today, based on what Kochen and Schalk found, is whether this concreteness fading idea is really a one-size-fits-all solution, especially when we're teaching math, physics, chemistry, and biology. The paper itself presents a really interesting challenge to that assumption. And for you, our listener who wants to really grasp this but values your time, we're going to try to distill the key insights without drowning you in academic jargon.
I think what's really intriguing here is that starting with concrete examples seems, very intuitive and logical. But this paper delves into the nuances of how we represent knowledge externally and how students learn differently across these STEM fields. So it makes you question whether one single method can truly cater to the unique ways these subjects are understood and taught.
So to kick things off and make sure we're all on the same page, let's define some of the important terms from the paper. First up, multiple external representations, or MERS. What exactly are we talking about when we say MERS?
Well, you can think of MERS as all the different tools and formats that educators use to present information to their students. I mean, this could be anything, like textbooks, written explanations, actual physical objects, diagrams, animations, even simulations. The core idea is that by presenting information in a variety of formats, we can support different aspects of learning a specific concept.
That makes a lot of sense.
Yeah.
So then we have the term concreteness fading itself. How do Kokkonen and Schalk specifically define that?
Okay, so they define concreteness fading as a particular sequence of instruction. It starts with concrete representations, so things that are tangible, you can touch them, they resemble real-world objects or experiences. And then step by step, you move towards representations that are more idealized or abstract. The idea is that this progression helps students learn better and also apply their knowledge in new situations.
And this approach, the paper mentions, has roots in Bruner's work, right? His ideas about how we represent things in our minds.
Absolutely. Back in the 1960s, Bruner proposed this system of 3 types of representations. So you have enactive, iconic, and symbolic.
Oh, wait.
Enactive is all about learning by doing through physical actions. Iconic is learning through visuals, like pictures. And then symbolic is using abstract symbols that don't really have a direct physical resemblance, like numbers or equations. And concreteness fading often kind of mirrors this progression, moving from enactive to iconic and finally to symbolic.
I see. So like if you were teaching fractions, you might start by having kids actually divide a real apple, so that would be enactive.
Right.
Then you could show them a picture of a pie chart divided into slices, that's iconic, and then finally introduce the written fraction, like 1/2, which is symbolic.
That's a perfect example. And another important term the paper clarifies is the definition of external representations themselves.
Right, so how do they define those?
Well, they define external representations as those objects in the environment that are purposely created to stand for knowledge, concepts, or even real things. And they highlight 3 key features of these representations. First, they're distinct from our internal cognitive representations, so our thoughts, our mental images, all that stuff.
Right.
Second, there's the act of representing itself, meaning the external object is a specific way of capturing or showing that target knowledge. And third, they're selective. They're designed to emphasize certain features or aspects of a situation and simplify things by leaving out other details. So the key takeaway for you is that these aren't just passive displays of information.
So like a map, for instance.
Exactly.
A map shows the streets and buildings, but it doesn't show the traffic or the noise or the people. It's a representation that highlights specific things for a reason.
Exactly. It's a selective representation. And the paper calls these external representations surrogates for reasoning, because our mental capacity is limited. So we often rely on these external aids to help us think through complex problems, like when we use a diagram to solve a geometry problem. And they make a crucial point that these representations are rarely used in isolation. We often use them together.
Which brings us back to those multiple external representations, the MERS. Now, the paper brings up Ainsworth's DEF-T framework. What's that all about?
DEF-T stands for Design Functions Tasks. It's basically a guide to using MERS effectively. It considers the design of the representations, like how many you use, what format they are, the order you present them in, which is, super relevant to concreteness fading. And it also looks at the different functions those representations serve and the cognitive tasks they're meant to engage the learner in.
So what are the main functions of MERS according to this DEF-T framework?
Okay, so the framework outlines three main functions. First, MERS can have complementary roles. Different representations can convey different information and support learning in different ways. So, for example, if you're trying to understand the human heart, a diagram might show you the structure and blood flow, while an animation could show how the muscle cells contract. They give you different but related pieces of the puzzle.
Okay, so different perspectives on the same thing. What's the second function?
The second function is constraining interpretation. If you're already familiar with a specific type of representation or it has certain visual cues, it can guide your understanding. Like if you see data presented as a line graph, you'll probably interpret changes in the line's height as changes in quantity over time. The representation itself kind of steers your thinking.
Interesting. And the third function?
So the third one is that MERS can help students construct a deeper understanding by allowing them to make connections and draw inferences. Analogies are a great example of this. By comparing a new concept to something they already know, learners can build more abstract and transferable mental models.
So the DEF-T framework helps us understand what these MERS can do. But the paper also delves into how these external representations actually affect learning and the cognitive processes involved.
Yes, absolutely. The authors argue that to truly get how we learn from MERS, we need a more precise model of the cognitive work happening in our minds, and they suggest that theories of analogical and relational reasoning can provide this framework, specifically Jetner's structure mapping theory.
Structure mapping theory. Okay, what are the key ideas there?
In a nutshell, structure mapping theory says that when we compare different representations, our minds go through several key processes. The paper highlights four. Abstraction, which is basically identifying the common underlying structure across different examples. Then there's re-representation, where we have to kind of change our mental model when a new example doesn't quite fit. Inference projection, where we use our understanding of one thing to make predictions about another, like in analogies. And lastly, difference detection, which is noticing the ways in which things that seem similar are actually different. So different teaching sequences will naturally emphasize different cognitive skills. Concreteness fading might really lean on abstraction and inference projection, but it might not adequately address re-representation, which is so important in physics when you move to a conceptually different model.
And that's a key point, right? Different sequences of MERS, like concreteness fading, might emphasize certain mental processes more than others.
Exactly. By understanding these cognitive processes, we can start analyzing how effective a teaching sequence like concreteness fading might be. And that leads us to the core of the paper. Does concreteness fading work across different STEM fields?
Now, the authors point out that external representations can differ in a bunch of ways, not just in how concrete or abstract they are.
Right.
Things like their dimensionality, whether they're static or animated, how familiar they are, all these things matter.
Definitely. Concreteness fading really hones in on this concrete abstract dimension, but even there isn't a universally agreed upon definition. Some researchers propose a two-step sequence, while others, like Fife and Nathan, define it as a three-step progression from concrete to idealized. To see how this fading works, the paper uses Fife and Nathan's definition as a starting point.
But the main idea, regardless of the number of steps, is this shift from concrete to abstract. Why is this believed to be so effective for learning?
Well, the reasoning is that starting with concrete representations taps into the learner's existing real-world knowledge and supports their reasoning. It could be because they can imagine actions or relate it to their experiences. Then, as you transition to idealized representations, the focus shifts to the core relational aspects of the concept. It aids generalization by removing irrelevant details. The fading is basically stripping away extraneous information, allowing the learner to focus on what really matters.
The paper uses a great example from mathematics to illustrate this, teaching 1/4. First, you use a physical pizza that you can cut, then you show a pie chart visually divided into fourths, and finally you introduce the abstract numeral, 1/4.
Exactly. The pizza allows for physical interaction. You can connect it to prior experience. The pie chart provides a visual, and then the numeral is the pure abstract symbol. This sequence can help students make inferences, like understanding that all three represent the same quantity, and it can help them abstract the concept of 1/4, so it's not just tied to a specific object.
So then, the paper goes on to discuss a framework developed by Lin and colleagues who tried to see if this concreteness fading idea could be applied more broadly across physics, chemistry, and biology.
Yes, they built upon the chemistry triplet. That's the macro scale, what we can see. The micro-nano scale, which is more about atoms and molecules, and the symbolic level, using chemical symbols and equations.
Right.
The idea was to see if moving from macro to micro to symbolic could be like a general version of concreteness fading for all of STEM.
But this is where the paper starts to present its main argument, right? This seemingly straightforward application of concreteness fading might not work in every domain.
Precisely. Kokkonen and Schalk argue that because representations and educational goals differ across math, physics, chemistry, and biology, concreteness fading might not be as universally applicable as some people think.
Okay, let's look at each subject specifically, starting with mathematics. A lot of research on concreteness fading has been done there. What are the key findings?
So in mathematics, the paper looks at a few studies. What's really interesting is that in many successful math examples, the representations used are very similar, sometimes even isomorphic, meaning there's a direct one-to-one correspondence. Think of that pizza and pie chart again. The pizza slices match up perfectly with the segments in the pie chart.
So the structure stays the same, even though the appearance changes.
Right. And the main goal in these math contexts is to help students grasp abstract symbols and notation. Those concrete representations, like blocks or counters, are kind of arbitrary. You could use different objects to represent the same idea. The fading helps strip away the specific details and highlight the underlying mathematical structure and its symbol. But the paper also notes that even in math, there are limits. Students don't always transfer their understanding perfectly across representations. Superficial features can be distracting, and sometimes they prevent students from seeing that deeper connection.
So even with similar structures, students can still struggle to make the link. How about physics? Does concreteness fading work the same way there?
Physics gets a little more complex. The paper mentions studies on teaching things like DC circuits, where the evidence for concreteness fading isn't so clear. Unlike math, where you have more freedom to choose your concrete representation, in physics, the concrete is often a very specific example of a law or principle, like an experiment with colliding carts to show Newton's third law.
And the more idealized representations in physics, like force diagrams or equations, they don't just remove visual details, do they?
No, they often introduce new conceptual information. In the Newton's third law example, going from colliding carts to a force diagram means you're now using vectors to represent forces, something you can't directly see in the physical interaction. The relationship between the representations isn't just about removing details. They each serve different purposes. They highlight different things. The goal is to understand not just the equation, but the physical event and how the representations model it. Let's consider this example to really see the difference in physics.
I see. So in math, the concrete representation is kind of a stepping stone to the abstract symbol. In physics, the concrete is a specific instance of a phenomenon, and the abstract is a theoretical model which comes with its own set of abstract concepts.
That's it exactly. The paper argues that, in physics, students need to understand each representation on its own and how they connect to each other and to the real-world phenomena they describe. It's not just fading the concrete experience, it's building this deeper, multifaceted understanding of the physics principles.
So let's move on to chemistry and this idea of the chemistry triplet. How does concreteness fading fit into that framework?
Right, so the chemistry triplet, with its macroscopic, microscopic, and symbolic levels, might seem like it aligns with concreteness, macro being the most observable, symbolic being the most abstract. But the paper argues that these levels are actually different levels of explanation, not just degrees of concreteness. Learning chemistry means you need to understand each of those levels. What you see, the underlying molecular explanations, and how we represent them symbolically. And importantly, you have to be able to move between these different explanations.
So it's not just about fading from seeing a reaction to understanding the equation. It's about understanding the molecular changes that connect those two levels.
Exactly. The paper talks about a study on phase changes, like water boiling, where using different sequences of macro, micro, and symbolic representations didn't really affect student learning. This suggests that the relationship between them is more complicated than a simple progression from concrete to abstract. Visual and spatial reasoning are also super important in chemistry, especially when you're visualizing molecules. And the goal isn't to see all representations as just different levels of the same thing, but to understand their roles in explaining chemical phenomena. And this includes emergent properties, where the macroscopic behavior arises from microscopic interactions in complex ways.
That's another big difference from the math examples, where the analogy was more direct. Okay, last but not least, how does concreteness fading apply to biology?
Biology is similar to chemistry and physics. You're dealing with multiple levels of organization within hierarchies and complex systems. The paper talks about a framework that involves components, interactions, and emergent behaviors. You could try to map these to concreteness levels, from a whole organism down to its cells and molecules. But the biochemical level, for example, isn't just a more abstract version of an organism, it's its own complex domain with its own unique entities and processes.
So you can't just fade from observing an animal to understanding its DNA like you might fade from an apple to a fraction.
Exactly. In biology, you often have nested hierarchies and nonlinear interactions, which makes a simple fading approach less applicable. However, they do talk about a study using computer simulations of ant foraging. In this study, a two-step concreteness fading sequence, going from realistic-looking ants to just dots, did improve learning. The authors suggest this might be because the detailed simulation helps students activate prior knowledge about agent-like behavior, which they could then apply to the more abstract foraging patterns.
So in that case, the initial concreteness helped them connect the concept to something they already knew.
Yes, but even in this example, the visual similarities between the representations were pretty strong, maybe more so than in some of those physics examples. So overall, the paper suggests that in biology, just like in physics and chemistry, students need to understand each representation and the often complex relationships between them, rather than viewing them as points on a concreteness spectrum.
Okay, so after looking at all these different STEM fields, what are the main reasons the paper gives for why concreteness fading might not be a universal teaching strategy?
They boil it down to two main points. First, the types of representations and the relationships between them differ a lot across domains. In math, concrete representations can be kind of arbitrary, but structurally consistent, and their purpose is mainly to support understanding of abstract symbols. In science, concrete representations are usually specific phenomena or experiments with inherent complexity, and the more abstract ones often bring in new concepts. The connections aren't always straightforwardly analogous.
That makes sense. What's the second reason?
The second reason is that instructional goals and the role of representations in achieving those goals also vary. In math, the goal is often abstract understanding and symbol manipulation. In science, the goals are broader, including understanding individual representations, how they complement each other, and moving between different levels of explanation. The idea of all representations being basically interchangeable, just with different levels of concreteness, doesn't really fit with these more complex goals in science.
So for our listener, to sum it all up, while teachable going from concrete to abstract seems intuitive and has worked well in some areas like math, this paper argues it's not a one-size-fits-all strategy for STEM.
Exactly. Whether concreteness fading works depends on the subject, the representations used, and the learning goals. The paper highlights fundamental differences in how knowledge is represented and how learning happens across different STEM fields.
This has been a really eye-opening deep dive into this research. It makes you rethink some assumptions about teaching in STEM. So here's a final thought to ponder. Based on this analysis, what could be some better guidelines for designing instruction in STEM beyond just concreteness? Maybe focusing on when to use analogies, emphasizing the complementary nature of representations in science, and considering the unique cognitive demands of each subject.
That's a great question. It pushes us to move beyond a simple, one-dimensional view of instruction and appreciate the complexity of representations and how they interact with learning in these different fields.
Thanks for exploring this important topic with us. We hope this provided a helpful shortcut to understanding this complex and interesting research.